Good morning, everybody, and welcome back to Next Door NetAdmin. So, in a previous week, not that long ago, just a couple weeks back, I talked a little bit about PROM, Programmable Read-Only Memory, and EEPROM, the electrically erasable variant, and I talked a little bit about flash memory as well. Now, in that, I mentioned that programming flash memory is pretty quick, because all you're doing is essentially stuffing a charge into a floating gate. And then the charge just stays there and it can be read, but that erasing is a much more involved process because you've got to essentially pull the charge back down out of the floating gate and then you have to reprogram it. So I thought today I'd go a little bit more into detail about how deletions work, not just in SSDs, but in general as well, so that we get a fuller picture of the context around this. So let's get started. When you delete a file, is it deleted right away? Your first answer is probably no, of course not. There's a recycle bin. But I'm not even talking about a recycle bin. I'm talking about when you actually fully delete the file within your computer's operating system, from the file system. What happens? Is the data actually like scrubbed and wiped out? No. For the most part, generally speaking, no, it's not. If you think about a spinning magnetic disk, why go back and actually erase the data off the disk? This was the thinking at the time anyway. Why would you do that? Your file system just has to mark the map of where data is on the disk and say, well, this one is now marked as free space. I can put something else in there. And then when you'd actually write data into that free space, that's when you would go back and actually overwrite the old file by writing a new magnetic pattern to the disk. There was never really a need to go back and demagnetize that section of the disk or set it all to whatever the equivalent of zeros was. That's just extra work. And so on a standard spinning drive, or what we would call these days conventional magnetic recording, there was never a need to do a full erase, generally speaking. There were specialized reasons in certain regulatory environments or, when a system is end of life, where it was good practice to go back and fully erase the entire disk, either by writing zeros to it or for some particular contexts, by going through and doing an actual data destruction technique, of which there are several, including one developed by the RCMP, the Royal Canadian Mounted Police. And so there is even a Canadian spec for data destruction that I'm aware of and have had to use in some contexts. But generally speaking, when you're erasing a file, the file is still there. You've just marked the disk map of the clusters on the disk and said, consider this one free, consider this one free disk space, consider this one free disk space as well. Okay, cool. How does this work in an SSD context? Is it pretty much the same thing? Well, it can be. But remember that when you're writing this in a file system, the disk itself does not necessarily know that what the file system is. It just knows that it has data of some type. And when you're doing wear leveling in an SSD, you're writing all over the disk. And that might include taking a sector of data and writing it elsewhere for optimization purposes. And because flash memory is easy to write, but more difficult to erase, if you are erasing a file, then you have to save the entire page, is what the technical term is for this. All of that data, and then write it back. But remember that when you're erasing something, you're not actually erasing the data. What you're doing is the file system is marking this as free disk space. And then it's not actually overwritten until you write something new in there. So let's see how this works in an SSD environment. Let's say you have 4 files, just for the sake of argument, 1, 2, 3, and 4. 1 and 4 on the end, we're going to keep those files. 2 and 3, we're going to delete. Okay. The disk doesn't know that 2 and 3 are deleted. It just knows it has data in a page, 1, 2, 3, and 4. Okay. The file system knows that, hey, 2 and 3, those are spare disk clusters now. They're free disk space. Okay. Well, now I want to write a new file in there. I'm going to write it where number 2 was. So from my file system's perspective, now I have 1, 2, 3 is free disk space. There's nothing there. And 4. But when I write that to the SSD only knows it has 1, 2, 3, and 4, and it needs to write new data to the space where 2 was. It doesn't know anything about 3. So what it's going to do is it's going to take a copy of that data. It has to erase the entire page, 1, 2, 3, and 4. Then it'll put the new data into 2's slot, but it doesn't know that 3 is free disk space. So when it writes it back, it's going to rewrite 1, our new file, in 2's spot. It's going to rewrite the old data from 3, which is free disk space, but the disk doesn't know that. And then it'll write 4 as well. So we've just erased and rewritten file number 3, which is deleted from the file system's perspective. But because the disk doesn't know that, we've rewritten data that we didn't need to, and therefore we've incurred more wear on the disk because we've had to erase it and then store more charges into the floating gate. And if we write a new file into 3's location at a later time, it's going to have to erase the entire page again, 1, 2, 3, and 4, and then rewrite it again because it didn't know that 3 wasn't supposed to be rewritten in the first place. Over time, this adds a lot of additional disk wear to an SSD. So, a command was introduced that lets the operating system tell the disk, consider this empty. You do not have to maintain any data in this section of the disk. The block is technically what it works on, the logical block address. And this command is called trim. So when the operating system marks its file system mapping as this is free disk space, this is free disk space, it sends a trim command to the disk that says, consider 2 and 3 as having been trimmed in this logical block address. So then, when you issue a write command to overwrite the space where 2 was stored, it goes, okay, so I need to actually maintain 1 and 4 in this page, and now I've got new incoming data for 2. I can actually squeeze this down into, a 3-block section, and maybe I can write that to a different section of the disk because I don't have to maintain the data for 3. It's been trimmed. So you can actually, over time, save yourself some of those writes. You're still writing out 1, 2, and 4, but you don't have to rewrite 3 in this example because you were able to tell the disk this has been trimmed. Don't worry about it. There's another interesting place where trim can be used, and that is on a new type of spinning disk which uses shingled magnetic recording. I mentioned earlier in this video conventional magnetic recording. Well, what's the difference between these, and how does that affect what we want to do? In conventional magnetic recording, you can think of it, and indeed the terminology is about sectors. You have rings, or what the disk refers to as cylinders. Cylinders, 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 cylinders. They're rings, essentially. And then you have sectors within those cylinders. And so when you write data, this is not something necessarily that the computer knows about, but the disk controller itself is going to say, okay, this logical block address is in this section of the disk, and it just writes that. That's conventional magnetic recording. Everything is in its own section. But there's a quirk in how these the actual magnetic heads that do the reading and writing of the disk, there's a quirk in how all of these are set up. You can read very easily, but when you're writing, you need to actually generate a proper current to get a proper magnetic field going that can actually remagnetize the sections of the disk. And because of that, your read head is typically fairly small. There's no need to make it big. You don't need it to be big. But the recording head has to be bigger because it requires more circuitry, it requires more power in order to be able to affect the disk. So your record head is big, but your read head is smaller. And some people had an idea. They went, okay, well, if my read head is this, and my record is this, why don't I just offset these slightly? Because if I'm recording this and reading here, then everything in here is wasted. So I could record another stripe starting here and read kind of in the halfway, rather than saying, okay, I need to move all the way over every single time. So because shingled magnetic recording is closer together, you get more data into the same physical disk size. But this also means that when you are recording new data, you are partially overwriting whatever you wrote before. That's why it's called shingled, because it kind of overlaps each time. And because of this, shingled magnetic recording actually needs to, when you write a file, okay, but if you record that, you're going to overwrite data on both sides, and that's going to affect the section that's being used for read on the previous track. So when you're rewriting shingled magnetic recording disks, when you write a new file, it actually has to go back to a section and it has to rewrite the entire section shingle by shingle so that everything lines up correctly. Which means if you have deleted data that the disk doesn't know about, then it's going to have to read what's there and then rewrite that entire shingle, even if the file system thinks, oh, well, this is free disk space. The drive doesn't know. And so with shingled magnetic recording, it's very important to have a command like trim so that the disk can say, okay, I actually don't need to worry about this. I don't need to worry about this. I don't need to worry about that. So as I'm rewriting these stripes on the disk, these shingles of data, I don't have to worry about rewriting this file. I don't have to worry about rewriting that. I don't even need to worry about reading it. It speeds up the operation substantially and possibly can save a lot of time, because maybe that data that you need can actually be rewritten in a different portion of the disk where it doesn't have to, rewrite all of the other shingles, or it can rewrite fewer shingles depending on how the disk is set up. Usually it won't be the entire disk that is shingled, because you'd end up having to rewrite probably most of, if not all of the disk every time you were overwriting something previously. So there's usually sections that are shingled so that you can go partway through the disk and start shingling that section, and you don't have to worry about affecting other sections endlessly down the line. So it is possible that you might be able to take some of that data and move it to the end of another section that hasn't been fully written out yet. That means you can just add on to what was already in that shingle, rather than having to overwrite and, rewrite the entire section. There's a lot of complexity that goes into managing data at the disk level. And fortunately for us, most of the time, we don't need to worry about that. You have a file system that operates at one level. You have maybe RAID or something similar like that. That's a different level. And then the disks worry about their own. I've given the operating system a list of logical block addresses, and I will manage how everything is written to those addresses. I'll manage how that goes to the actual physical hardware, because I understand my own disk geometry. I understand what is required to move data in various places for wear leveling or for reshingling a section. And you don't need to worry about all of those details. Where you do need to worry about some of those details is in the application. As an example, shingled magnetic recording is great for disks that you're writing once and then you're never modifying, or modifying very infrequently. It's a terrible, terrible match for something like a NAS. No matter how much Western Digital tries to claim otherwise, it doesn't work well to have shingled magnetic recording in a NAS, because you're writing, rewriting, and modifying data all the time, especially if you're using a file system like ZFS, where you're using variable stripe sizes, so it's not always going to be the same RAID stripe size, and where it's copy on write, you're explicitly copying rather than overwriting data for the most part. And you're balancing a whole ton of stuff. SMR disks are very bad for that. It gets a little better if they have support for trim, but you still don't want to use it in that particular application. Similarly, the advantages of Flash are amazing. The speed is faster, it's very reliable, you don't need to worry as much about spreading your data over a whole bunch of disks to speed up access by parallelizing everything. You get a lot of that benefit from just using flash drives. But you do want to make sure that they have trim support, and you want to make sure that your operating system has trim support as well, and that it's enabled, or else you won't see the advantages of trim at all if any of those are not present. If the drive doesn't support it, no use. If the operating system doesn't support it, you can't tell the drive about it. And if it does support it, but it's not enabled, it's not going to tell the drive about it. So this is why a lot of these lower level details are not necessarily things that will affect an admin in the day-to-day, but it's really important to take account of when you're planning a system to make sure that you are getting all of the performance that you think you should be getting, to make sure that you don't accidentally choose something which is suboptimal or is just not going to work at all. So it's really useful to keep these things in mind and to understand enough about them to be able to account for it when the right time and the right circumstances arise. So there you go. Hopefully that has been interesting and enlightening for you. If you have thoughts on other things that you would like to hear me talk about or things that you would like to see me demonstrate, feel free to let me know right down there in the comments section. Otherwise, thank you very much for watching. I am your next door NetAdmin, and we will see you next time.